Okay, here we have a power series. So we have a function, okay, and this is the power series. And we don't want the all the coefficients in principle. What we just want is three coefficients, but they are with coefficients with a high index here. Well, the definition of this coefficient is easy, right? According to the formula, Taylor formula. This is just fn of 0 divided by n factorial. So all we need to do here, in principle, is take n derivatives, right? Substitute at 0, and then divide by n factorial. But if we try to do this with this function, then you very quickly end up in troubles. And the reason is, well, this is a question. Now, every time you do this, you will have a rational function more and more complicated. So at the end, taking the derivatives is painful, and you don't have a clear pattern from which you can extrapolate this. So clearly, we need to use a different procedure to evaluate these coefficients here. And the procedure is suggested by what you have here. Okay, if this is the let me see, if you have this identity here, right, then what you can do here is this. You can divide this here and divide this here, and then write this rational function as 1 minus x over 1 minus x cubed. All right? Which is equal to 1 over 1 minus x cubed minus x over 1 minus x cubed. And both these functions are easy to expand in powers of x. This one because it's related to the geometric function, right? The geometric series, where you take this equal to w, for instance. This is the geometric series. And this one is the same as this one, but multiplied by x, which is just multiplying a power, right? So let's try to do that. So the first series here is the sum from n0 to infinity of x cubed to the power n. And the second series here is x times the same series, so x cubed to the power n. Now, the first series is just x 3n, right, multiplying the powers. And the second series is x to 3n plus 1, because we also have to multiply by this x here. Okay, well, this is the expansion, right? This is the expansion. If you want to write this as a common expansion like this, an x to the n, right? Well, let me call the index in a different way to avoid confusions. Okay, xk, x to k. What we have is the following. Ak is equal to, if k is a multiple of 3 for some n, then the coefficient is 1. Okay, coefficient is, well, the coefficient of this, which is 1. If k is a multiple of 3 plus 1, again for some n, then the coefficient is negative 1. And if k is 3n plus 2 for some n, then the coefficient is 0, because there are no terms in this series which are of the form 3x to the 3n plus 2. All right? So this is the coefficient ak, right? Which means that the corresponding derivatives, so fk 0 is equal to k factorial if, because we have to multiply by this, right? K factorial if k is a multiple of 3 is minus k factorial if k is a multiple of 3 plus 1, and 0 if k is a multiple of 3 plus 2. And now we just have to look for the question here. We need to find the coefficient A300, right? So what is A300? Well, it's 300 is divisible by 3. It's of this form, right? So A300 is equal to 1. Then we have A301. 301 is of this form here, so A301 is equal to -1. And then we have A302, which is equal to 0. And that is the answer to this problem, okay? So if you try to do it brute force using the formula, you don't get very far, because taking derivatives of this function is painful. And it's very hard to find a pattern that the derivatives follow, okay? However, if you apply this simple trick, I mean, you rewrite this as this fraction here, then it's very easy to divide this into this series, and each of them is easy to calculate. And what you end up having is this, which is telling you that only powers which are multiple of 3 or multiple of 3 plus 1 are non-zero. And if you group them in a single expression like this, then these coefficients are just 1, -1, or 0, depending on whether the exponent is proportional to 3, proportional to 3 plus 1, or proportional to 3 plus 2, right? So that's it. And that way it's very easy to calculate these three coefficients that appear here.